In this video, I'm going to talk to you about variation of parameters for solving non-homogeneous second-order linear differential equations. And as this is example 0, I'm going to talk big picture, which is I'm going to work in the most general of cases, and we're going to derive some formulas that are very important, and we're going to talk about where these formulas come from. And 3 additional examples 1, 2, and 3, I'll work through actual problems by using the formulas that we derive in this video. Yeah? Cool. All right, let's get started. Now, since we're working with a non-homogeneous equation, we know that we're after a particular solution. And let's say that the particular solution has the following form, which is that it's some function v1 times y1 plus some function v2 times y2. And so what we're trying to do in variation of parameters is find out what the functions v1 and v2 will have to look like, because y1 and y2 we assume we already know. y1 and y2 come from our complementary solutions. So y complementary is like alpha times y1 plus beta times y2, where alpha and beta are some constants, and y1 and y2 are the solutions to the homogeneous equation. That is, if instead of d of x we had 0, then plugging in y1 here, y1 prime and y1 double prime in those 2 other places would get this equation to actually say equal to 0. It would get it to equal 0. That is, y1 is a solution to the homogeneous equation. And likewise y2. So if I plug in y2 there, y2 prime there, and y2 double prime there, then I'd get equal to 0 also. All right, that's what we're saying about y1 and y2. Remember this, very important. They're the solutions to the homogeneous equation. Now, we're working with a particular solution which solves the non-homogeneous equation. So if somehow we found out what yp prime is and yp double prime is, and plugged in yp double prime here and yp prime here and then yp here, then equality is maintained. That is, the right side will equal d of x. Yeah, cool. So that's the solutions we're after. So let's find what yp prime is and then yp double prime thereafter. So yp prime is going to require we do product rule there and product rule there. Doing both correctly, we write v1 prime y1 and then plus v1 y1 prime, and then plus v2 prime y2 plus v2 y2 prime. Yeah, and here we're going to make an important assumption that's going to give us a constraint on v1 prime and v2 prime, and additionally simplify our expression for yp prime significantly. And that assumption we make here is going to be that v1 prime y1 plus v2 prime y2 be equal to 0. So with this assumption, notice that we could get rid of that guy and this guy and reduce the expression for yp prime significantly, right? And to that, just that, right? Okay, cool. And now that means that our calculation of yp double prime is going to be easier. And again, we need to do product rule there and there for yp double prime. And so we're going to say v1 prime y1 prime plus v1 y1 double prime plus v2 prime y2 prime, and then plus v2 y2 double prime. Cool. Now look here, we're gonna write a of x times yp double prime, right? So yp double prime plus, and then it's gonna be b of x times yp prime, right? So yp prime, and then plus c of x times yp, and we're gonna say that since the particular solution solves this non-homogeneous equation, that it equals d of x. But in this expression, lots of stuff simplifies, and here is how. Let's look at what these terms look like a of x times yp double prime. And so it's basically writing a of x times yp double prime is like writing a of x here, a of x here. Let me actually, for simplicity, just write a. Is that okay? I hear you nod, or I see you nod. So I'll just write a, right? Okay, they will all have a of x. And then let's look at these guys. These guys are basically b of x here. And so let's just write a b there and a b there. Cool. And then finally, let's write yp with c here. So c of x here, right? And then, so that's a c there and that's a c there. But now, if we look at all the terms that only have v1 in them, right? Because here, like, we're adding all three terms. And if we look at all three terms, right? And that is if we look at actually all of these guys, and then all of these guys, and then all of these guys, and figure it out, all the ones that have v1 in them, right? First, because they would all have v1 in them, we can factor out the v1. And those would be this guy right here, and then let's see, who else? This guy right here, and then this guy right here, right? Then once we do that, once we take out the v1 from all three of them, look at what we have. We have v1 times a y1 double prime, that's from that guy, and then this guy will say b times y1 prime plus b times y1 prime, and then plus the last guy is c times y1. Remember, we've taken out the v1, so c times y1. But wait, we said y1 is a solution to the homogeneous equation, and this here is this here with y1 plugged in it. So it equals 0, because I stressed at the beginning of the video that y1 plugged in there gets it to equal 0. So we see that this here is exactly that, which is y1 double prime plugged in there, y1 prime in there, and then y1 in there. Yeah, cool. So basically we have v1 times 0, and therefore 0. That means all of the terms containing v1, we can get rid of them, right? Okay, and these are the only terms containing v1, so that's it. Okay, so let's see, that means we can get rid of, let's actually literally do it, get rid of that, and then it means we could get rid of, that's a plus, so it doesn't matter if I take the plus sign away, right? We could get rid of that. And then lastly, we could get rid of, well, I'm not going to get rid of it from up here, but I'll write a crossed out so that you know that it's gone. So that, right? Actually, I'll get rid of it. Let's just write our particular solutions form somewhere else. So yp is equal to v1 y1 plus v2 y2. And what we have over here is c of x times yp. All right, and what we just said is we could get rid of this guy, right? So let's actually do it. There you are. Go away. Okay, there it is. And now, for very similar reasoning, we can get rid of all the terms containing v2, because look at them. So that it's that guy, and then where's another term? That guy contains v2 right here, and then that guy. And if we take out the v2 from all of them, look at what we'll have. We'll have v2 taken out, and then we'll get a times y2 double prime from this guy, right? And then this will be b times y2 prime, and this will be c times y2, but you guessed it, you see where this is going. So this is b times y2 prime, and then plus c times y2. But wait, y2 is also a solution to the complementary, meaning it gets the homogeneous solved. So it would have solved if instead of d of x we had equals 0. So this whole thing is 0, meaning we have v2 times 0, which is 0. So we can get rid of all of the terms containing v2, and these are it. This is all of them. So all right, hopefully it doesn't get rid of this. Yeah, okay, needed to get rid of that. So anyway, now what does that mean? v2 terms we can get rid of, so that's that. And then v2 term is this guy, right? So that's that. Okay, so this simplified a lot. So we just have that, and then this guy's everything is gone, right? And we v2 term, right? This guy, everything is gone. So the only survivors are are and once we plug in, it's supposed to equal d of x, right? So the only survivors from all of this are the a of x terms, and specifically these two a of x terms. Otherwise, this is gone, this is gone, so we just have these two terms equaling d of x. Okay, cool. So that's to say we have a of x, right, times, we have a of x times, and then it's, and that's the a of x I'm factoring out. And then we have v1 prime y1 prime plus v2 prime y2 prime. We have that this equals d of x. Now, in all of the examples you will work out, I urge you to do this, which is if the coefficient of y2 double prime is not already 1, so if you have something other than 1 in front of y2 double prime, then immediately divide by that thing everywhere. That will be the case in example 3 in my videos. But yeah, we divide by a of x, and this is why, because and the formulas that I write that are about to come, we call a of x, we call d of x divided by a of x, we call this f of x. And so then my formula will agree with your problem only if the coefficient in front of y double prime is 1. And of course, you can always make that happen by dividing by whatever's in front of y double prime, which will mean that, you know, if you called what was originally to the right of the equal sign d of x, then d of x divided by the a of x will be your f of x. Of course, if the coefficient of y2 double prime is 1 to start with, you just call whatever is the right side of the equal sign f of x, yeah? Basically, in my formulas to come, I call d of x divided by a of x f of x, yeah? Okay, cool. So with that handy, then we can write this second and all-important constraint on v1 prime and v2 prime, and we can move forward with life. We're almost done. So now we've got a second constraint on v1 prime and v2 prime, namely this, right? Equals f of x, right? Now, told you f of x is that. Yeah, okay. Which is always the right side of the equation in your problem if y double prime has a coefficient of 1. Yeah, okay. All right. Anyway, I've said enough about that. So let's move forward with solving this system of equations in two unknowns, and we'll finally be done, right? Because now we see that this is a system of two equations and two unknowns, where the two unknowns are v1 prime and v2 prime. And if we can solve for v1 prime and v2 prime, then we can solve for v1 and v2. We just take the integral of v1 prime and v2 prime respectively, right? Okay, so now v1 prime is equal to, I'm going to use Kramer's method for solving. So using Kramer's method, it's going to say it's the following. And for v2, it's going to say something similar. So v2 is the following, and v1 is the following. v1 is, by Kramer's rule, do I really need a ruler for this? I'm being annoying, but yeah, neatness matters. Okay. Well, so does efficiency, and I just like messed up on opportunity to be efficient, which is drawing another one down here. Okay. How about learning from my mistakes? Right there, right there. And then right there, and right there. And actually, sorry y'all, need more room. So right there and right there. Okay, so first v1 prime, right? By Kramer's rule, it's going to be the determinant of the matrix with entries 0, f of x, and then it's going to be y2 and y2 prime, right? Okay, cool. And then the determinant in the bottom is going to be y1, y1 prime, y2, and y2 prime, and it's the determinant of the same matrix in the bottom of v2, y1, y1 prime, y2, y2 prime. But wait, we recognize this determinant. It's a Wronskian, right? It's a Wronskian. So we see first that v1 prime is going to be, by doing the determinant there, it's going to be 0 minus y2 times f of x. So negative y2 times f of x divided by, we just said this determinant is the Wronskian, which is w of y1, y2. So the denominator is, poor, w of y1, y2. And so here for v2, it would be, let's see, for v2 it's going to be, we're going to say y1 prime, and then 0 f of x. So this time we're going to get y1 f of x, right, minus 0, so nothing, divided by the Wronskian again, so w of y1, y2. So unsurprisingly then, we're going to get the following. Since this is v1 prime and this is v2 prime, we're going to get the following solutions for v1 and v2. So v1 is going to equal the integral of negative y2 f of x divided by the Wronskian of y1, y2. And then dx, of course. And then v2 is going to equal the integral, you get it, of y1 f of x over the Wronskian y1, y2 dx. Okay, cool. These are very, very important formulas, as you need to frequently find v1 and v2. And then finally, the particular solution is going to be, it's going to be, well, we already wrote it, right? The particular solution is going to be this guy right here. It's going to be v1 times y1 plus v2 times y2. Now, if you're able to find these integrals, remember that they come with a constant, let's say plus a and plus b, and that's saying that you've found this integral and you've found that integral. So when you multiply v1 by y1, right, then it looks like you also need to have a times y1. But you don't need to do that, because y1 times a, and then for v2, what we would have said is that you need to have, in addition, you need to have a plus there, and then you need to have y2 here, right, for v2, y2 right there. But then that'd mean it's actually not a there. I would want b, a different constant, just to distinguish. So we'd have b, and then we'd have by2. But notice that y1 times a and then y2 times b are already included in our complementary solution in alpha times y1 plus beta times y2. So you actually, in finding these integrals, do not need to find, you do not need to find constants or write the constants. So it's sufficient for you to say that your particular solution is simply this, which is that your particular solution yp is equal to y1 times v1. Sorry, I want to include the dx, and then plus y2 times v2. Yeah, cool. All right, this is good enough for a motivation video, and I hope you enjoyed it. And watch the examples, which are shorter, and show you how to actually solve problems. But I hope you still enjoyed this. Take care.